Algebra 2 Cram, New York State, Algebra 2 Regents, Common Core, Basic Graphs of Inverse Trigonometric Functions. The domain of the inverse cosine of x, sometimes called the arccos of x. Concept number 15. Now, the odds of someone doing exactly what you tell them to do is pretty slim, but I guarantee that if you cram with me, you'll become an Algebra 2 master. Inbox me at memedicine@gmail.com to order this complete cram session. If this isn't the topic you're looking for, no worries. Still inbox me at memedicine@gmail.com to order personalized packages. Be sure to spread the word to your friends and classmates who also need to cram. Let's cram the concept of the domain of the inverse cosine of x. Basic graphs of inverse trigonometric functions. Domain of the inverse cosine of x. Okay, so the key to progressing through this really well is to put things in order. So I'm going to give you a pre-example before we get into the actual concept. This may take a little while, but not too long, okay? So where our angle of interest here is theta, we're going to call this angle theta rather than x, as shown here, because we don't want to double up on variables. I'm going to use x as the x coordinate, all right? So here we have our x, y Cartesian coordinate plane, and you see here an acute angle in standard position. When I say standard position, these are the features of an angle in standard position. First, the vertex is at the origin. The initial side ray, whose extent is the x-coordinate, is on the positive x-axis, and the terminal side ray, whose extent is the y-coordinate here, ends in quadrant 1 between the bounds of the quadrantal angles 0 degrees and 90 degrees, okay? And just note, because you're in quadrant 1, the x-coordinate can be positive, as well as if you were in quadrant 4. And because you're in quadrant 1, the y-coordinate is going to be positive. It's also positive in quadrant 2, but negative in quadrants 3 and 4, and the x-coordinate is negative in quadrants 2 and 3. Okay? Keep this in mind because it's going to be important in the future when you're dealing with cosine. Now this acute reference angle, well, I just gave what I was saying away. This acute angle, theta, is also referred to as a reference angle, sometimes called theta ref, sub ref. Okay, and the reason is because when you calculate the inverse trigonometric functions of specific angles, what you're getting is an acute angle that would occur in quadrant 1. All right, and this fits all the features. Your graphing calculator, that's what it's going to give you, or your scientific, whichever one you're using. But based on the parameters of the question stem you have, you're going to have to determine, well, is this the angle I'm looking for? For example, let's say theta reference is 40 degrees. And let's say we were to do a vertical flip about the y-axis, like so. Well, what you're most likely, or you could be interested, is not actually in theta, but you're probably going to be interested in this obtuse angle here. So the way you calculate what you're actually looking for, the angle you're actually looking for when it falls within quadrant 2, but you're getting an answer of the theta reference in quadrant 1, is you're going to subtract theta from the extent of quadrant 2, and the quadrantal angle that cuts off quadrant 2 is 180 degrees. So 180 degrees minus our example theta of 40 degrees is going to yield a value of 140 degrees. Okay, let's continue in this vein of thought. Let's say that you did a diagonal flip about the origin and you ended up with your theta over here, and you calculate the inverse trigonometric function. It could be cosine. Okay, but let's say that you're not necessarily interested in the answer theta that you're getting, rather you're interested in this obtuse angle. What you would have to do in this situation is add theta reference to the extent of quadrant 2 rather than subtracting it. So you're going to get 180 plus 40 degrees because 40 degrees is the example theta that I'm using here. And that's going to be 220 degrees. Okay, so last but not least, let's say you have a horizontal flip about the x-axis and you end up with theta over here, but you know that although you're getting an answer of 40 degrees for x or theta, whatever variable you're using, that's not what you're interested in. What you're interested in is the angle that's occurring in quadrant 4. So let me show you what you would be really interested in. Well, this big guy here. So in order to calculate that huge obtuse angle, what you would have to do is subtract theta from the extent of quadrant 4. The extent of quadrant 4, which also, parallels 0 degrees, is 360 degrees. So 360 degrees minus a theta of 40 degrees is going to give you 320 degrees, okay? So that was a long aside, but now what I want to show you, I want you to realize that the inverse cosine function comes from the actual cosine function, okay? And the cosine of theta or x, whichever variable convention you're using, is just going to be the x-coordinate, which can be positive or negative, divided by the terminal side array, also called the hypotenuse, or the longest side of the triangle. And it's divided by the magnitude of the terminal side array, because here we're actually measuring the measurement of the distance of this ray, so it's always going to be positive. Only the x-coordinate or y-coordinates can be positive or negative, okay? And the reason being is because this right triangular formation is just the resolution of that whole terminal side array into its x and y coordinate, okay? That might have confused you a little bit, but don't worry about it. All right, so yeah, the cosine of the specific angle theta is going to be the bottom side or the adjacent side or the x-coordinate divided by the hypotenuse, okay? All right, but let's explore the inverse cosine concept. The inverse functions undo cosine functions or sine functions or tangent functions or cosecant functions, secant functions, in order to yield the actual identity of the original angle of interest, okay? So if you were to take the inverse cosine of this entire equation, you're going to have to distribute the inverse cosine, obviously, on the left-hand side and the right-hand side. And when you do that, you get the inverse cosine of x over r is equivalent to the inverse cosine of the cosine of theta or x, whichever variable you're using. Here we're using theta, but I just included x, so you can know that, yeah, you can use that as well. And what you're going to end up with is the inverse cosine of x over r is equal to theta, okay? The angle. So taking the inverse cosine of a cosine just undoes the function and yields the value of the angle. Okay, that's what I wanted to demonstrate to you in the pre-example. So it did take a little while, but thanks for bearing with me. And if you don't like sitting through these whole things, play it on double speed. You'll probably understand just as much as if you were to play it really slowly. Play it on double speed a few times throughout the day whenever you have time, whatever works for you. Okay? All right, now for the actual concept. What is the domain? And when I say domain, I mean the set of all possible x values or independent variables for a function. Of the function y equals the inverse cosine of x, sometimes referred to as arc cosine of x. These are the same functions, okay? So definitely press pause now and draw out your answer in the form of a graph to demonstrate your reasoning. And if you don't know what the heck is going on, that's completely fine. Just sit tight. We're going to go through it together. Okay, so hopefully by now you press pause and were able to come up with an answer. If not, let's try this out together. All right. So what I want you to know is that, I think I mentioned this already, is that y equals the inverse cosine of x is the inverse function of the original function y equals the cosine of x. Okay. But since the y equals the cosine of x is not a one-to-one function, what I mean is that it's a function because it passes the horizontal line test. I mean, the vertical line test, it doesn't, pass through it twice. So any function graphed on a Cartesian coordinate or coordinate system that passes the vertical line test is a legit function, okay? But that doesn't necessarily mean that it's a one-to-one function. One-to-one functions have to pass the horizontal line test. Let me show you what I'm talking about. It does not pass it because you can cross, like several elements in the domain can have the same dependent variable or y value. So that's not a one-to-one function, okay? And for us, that's not good in crafting the domain of our inverse function. So what has to happen is the domain of the original trigonometric function, the cosine of x, has to be restricted, like so that ultimately the inverse cosine function can be a legit function. That might be a little confusing, but I'm going to show you exactly what I'm talking about. Now you can restrict the cosine of x domain any way you want, but typically in algebra for this type of concept, the cosine is restricted between 0 and pi, okay? So this is approximately increments of pi over 3. All right, that's what's typically done. And this also leaves the range restricted between -1 and 1. But whether it was restricted or not, the range of the cosine function is always -1, 1. So that remains unchanged, okay? Now, to create the graph of y equals the inverse cosine of x, you're going to have to reflect the cosine of x, the restricted function, across the line y equals x. And in doing so, basically, you're going to interchange all the x and y values. So in essence, you're interchanging the domain of y equals cosine of x to make it the range of y equals the inverse cosine of x, and you're interchanging the range of y equals the cosine of x to make it the domain of y equals the inverse cosine of x. Hearing this initially is a little confusing, but it's going to be very clear once it's demonstrated on the graph. Okay, so after reflection over the line y equals x, we get the graph of y equals the inverse cosine of x. So basically, we took this bad boy and we flipped it like so, okay? You have to be able to picture this revolution in your mind. Some of you can't right now, some of you can. It's just a matter of daydreaming or exercising your imagination muscles, which is just very important in life in general. So if you don't, and actually, a lot of people daydream by default. We dream about the future, specifically things that we don't want, like failing a math test. What you want to do is stop that, like, because you're ruining your life. What you want to do is to imagine always what you want, whether or not it seems impossible. And if you don't know what to imagine, imagine this rotating about the line y equals x. Okay. Again, notice that for y equals the cosine of x, the domain is -1, 1 to 1, okay? And the range is from 0 to pi. If we consider these every increment pi over 3, okay? All right, this might be a little too hectic for you, so let's just neaten things up. So here we have, again, the domain, that's the answer that we're looking for, is between -1, 1, including the endpoints. -1 and 1, that's why they're shaded. So the domain of the inverse cosine of x, or the arc cosine of x, is going to be -1 is less than or equivalent to x is less than or equivalent to 1. All right, thanks for tuning in.